Hi! In this video, I'll be going through what are known as modules, and I'll show the link between modules and vector spaces. And so first we must define what a module is, and we say we let R be a ring. It may not be commutative and it may not have an identity. It's just a general ring, and we can say that a left R module or a left module over R is a set M together with a binary operation on M, under which is an abelian group. And then you must have an action on M. So this is like a group action that follows specific properties such as distributive, associative, and you must also be able to distribute in M. And then if the ring has 1, we oppose the additional condition that 1 sends M to M. So you can define and write R module analogously, and if the ring is commutative, then of course the left and right is the same. And so if R is not commutative, then in general axiom 2b will not hold. And you can check it out yourself. When R is a field, the axioms for the R modules, if you see, are precisely the same for vector spaces over fields. And so modules over fields and vector spaces over fields are the same thing. So modules generalizes it into a sense that it's just over a ring. So we let R be a ring and M be an R module, then a submodule of M is a subgroup that is closed under the actions of the ring elements. Meaning to say, Rn is an element of N for all R and N. And so the submodules are just subsets of M, which are themselves modules when restricted to the correct operations. And then you just see that if R is a field, then the submodules are just the same as the subspaces. And every module will have two submodules, namely itself and 0. And 0 is known as the trivial submodule. So you can see it's not very complicated because you have a very concrete example of vector spaces that you have studied before. If not, you can just take this as a new definition and we'll learn together. Let's see some examples. So we let R be any ring, and we say that, and if we let the set itself be R, then it itself is a left R module, where the action is just the usual multiplication. So R can be considered a left module over itself, and the submodules are the left ideals of R, because you want it to be closed in your action. And if we let F be a field, then the vector space will be a module, and the submodules are of course the subspaces, and you can see it over here. And so we can have many type of examples, and one more example is the one known as a free module. So in this case, a free module is just a module that has a basis, just like a vector space having a basis. A free module is one where it has a basis, and we say the number of elements in the basis set is the rank of the module. And the same abelian group may have a structure of an R module for different types of R as well. So it's not like for instance, the field of reals is a R module, a Q module, and a Z module. And one more thing to note is that every abelian group is a Z module. So in this sense, because we already start off with a abelian group, all our modules are all our R modules are also all Z modules, where Z is integers. And if we see that when I is a maximal ideal and Im equals to 0, then M is just a vector space over the field Ri. And you can see it from this, how we get that defining action. So one most important thing is Z modules. And if we let A be any abelian group, we can always define the action as the following. And this action of the integers makes A a Z module. And this is the only possible action of Z. So, every abelian group is a Z module. And conversely, if M is a Z module, then M will also be an abelian group. And so Z modules are exactly the same as abelian groups. So now we shall state a proposition and prove it, where is of course the submodule criterion. Like how we have subspace criterion, we have a submodule criterion, and a subset of M is a submodule if and only if it's non-empty and it satisfies this condition. So you can see it's very, very similar to when you do vector spaces. So this should be maybe easier, but if it's your first time, then take it slow. So if N is a submodule, then of course 0 is inside N, so N is non-empty. It's also closed under addition and the action, so you're done. Now conversely, you suppose that 1 and 2 holds, and we just let R equals to -1 and apply the subgroup criterion to see that N is a subgroup of M. In particular, 0 will be inside N, and so we let X equals to 0, and then we apply hypothesis 2 to see that N sends to itself under the action of R, and this established that it is a stub module. Next, we will talk about quotient modules and module homomorphisms. And it's very similar to group homomorphisms and ring homomorphisms already. And so we say a map is an R module homomorphism if it respects the R module operation. So it first must respect the group operation of M, and then it must respect when you scale it by R. So R times X, when you send it, it will be R times phi of X. And it's an isomorphism if this homomorphism is bijective. Because a bijective homomorphism, the inverse will also be a homomorphism. So we can just say that a bijective homomorphism is an isomorphism. If phi is an R module homomorphism, then the kernel of phi will be the elements in the module that are sent to 0, and of course the image will just be the set that it hits as usual. So some examples to see is if R is a ring and M is the module over it equals to R, which is a module over itself, then R module homomorphism need not be ring homomorphisms. And ring homomorphisms need not be R module homomorphisms. And so the classic example, you can see if it's R equals to Z, the Z module homomorphism from X to 2X is not a ring one, because 1 is not mapped to 1. And when you have a ring homomorphism, it might not be a module homomorphism. So there's no like interlink between the rings homomorphism and the module homomorphism in general. And if R is a field, then the R module homomorphisms will just be known as the linear transformations. And when are the module homomorphism the same as the group homomorphism? It's in the case where it's a Z module. Then it is exactly the same as the abelian group, as we have already noted that Z modules are the same as abelian groups. And so the next proposition is a criterion to state when it is a homomorphism, an R module homomorphism, and it must respect the addition and it must respect R. So you can have one shot, you can just write this if you can prove it. And with that, we can now define when two homomorphisms a new function, and this will also be a homomorphism between M to N. And so the multiplication will also be, if you multiply these two functions together and with the following, in a sense that it will be just R, you take out the scalar times phi of M. And this R phi will still be our R module homomorphism. And actually this shows that the group of homomorphisms is an R module. Next, I'll leave it to you to read and check that compositioning two homomorphisms will still be an R module homomorphism. And in the next part, we will prove that every submodule of R module M is normal in the sense that we can just always form the quotient module. So we don't really need to see that it's a normal group, but you can just always quotient of the submodule. And this really stems from the fact that it's already an abelian group from the start. And it's closed under the action. So the reason is because it's first of all an abelian group. So every submodule is automatically a normal subgroup. And so you can already form the quotient map. And any module homomorphism of abelian group is already seen. So what we just need to check is that the module's action is compatible with the group homomorphism. And so proposition 3 tells us that it is. So we let M be an R module and N be a submodule of M, then the quotient group is M over N can be made into an R module by defining the following actions. And we see that the natural projection map is an R module homomorphism with the kernel N. And we are done. So the proof of it is very simple because we already know Mn exists and we just need to check that this action makes Mn an R module. So to check there is an R module, We just need to show the following steps. And you can just check through the axioms and you'll be done. As for the projection map, you can again check that it is a module homomorphism because pi times Rm will equals to Rm plus n, and Rm plus n is just R bracket m plus n because this R is in n, then m plus n is just the pi of m, so we're done. And this shows that it's a module homomorphism. And so lastly, we have of course analogous statements for the isomorphism theorems, but now for R modules. And we can just define the sum of two modules, submodules, to be this following. And you can actually just check that it is indeed the smaller submodule containing A and B. And so we shall just state the isomorphism theorems, as the proof of it can be found in the textbook, and the proof of it is very similar to group isomorphism theorems and ring isomorphism theorems. So there's not much details that you already don't know. You just need to read it in the book if you want to, but you can just take it that these are true because you've already seen it in group isomorphisms and ring isomorphisms, and there's not much difference in the proofs. So I shall just state the isomorphism theorem, and the first one of course is stating that the module divided by the kernel will be isomorphic to the image. And phi is just a module homomorphism. And the second isomorphism theorem states that A plus B, quotient of B, will be isomorphic to A quotient of A intersect B. And of course the third one is if you quotient A by A in the numerator and the denominator is the same. And the fourth one just gives us a bijection between the submodules of n containing n and the submodules of m divided by n. So this is an introduction into R modules. I've hoped you have understand what are modules now, and you can see how they are closely related to vector spaces when the ring that we consider is a field. That's all for this video, and in the next one, I'll be going through some more structure theorems about the modules. See you in the next one. Bye!